Hello everyone. Today we are going to discuss about the Bloom filters. So Sunny is going to explain us what Bloom filters are, why they work, and in what situations and in what use cases we should be using them.
Cool. Thanks, Puljit. So let's first understand what is Bloom filter. So I have went through this document. I'll skip through certain parts, but I'll try to explain it. So Bloom filter, as I say, is a probabilistic data structure. So it's a data structure used to solve certain problems related to probability. So a few things that we can say is like, let's say you want to do spam check on based on certain words. So that can be done using this data structure. And the concept is very simple. We'll see how. So it's based on hashing techniques. So we know a lot of hashing algorithms like MD5 or SHA-1, right? SHA-256. So which can be used to hash your data into, let's say, an array. So basically what it does is you hash your existing spam data, which you know it's a spam, into an array. And when you want to check for a particular data point, whether it's an spam or not, you again check back into your array whether it's present or not. If it's already present, you say that it's a basically it's a spam. Now,
So can I use it for such use cases only where I need to just where the answer is either yes or no, or can I store the value as well?
okay, well, you can store a value as well, but I think the problem is multiple things can hash to the same index in the array. So then which value you will store? If you are doing some count or something, then probably you can do it. But otherwise, it does not have that kind of use cases.
So use cases basically for
Yeah,
checking
yeah,
where something exists or not, something is true or false or not.
yeah. Some kind of pattern thing, right?
Okay.
So why probabilistic now? Like here in the definition we are saying, right, ki, if it matches to the same hash value, then why are we saying probabilistic? So I think if we look at the hashing, so we know that if we're hashing the value, then there are chances of collisions. So what it says is ki, when we are testing for an element in this data structure, false positives are possible because I might have hashed another key which might have hashed to the same table at the same index, but the current value was not present, but we detected it as a present value. So that means it's a false positive. But if some element is not present there, then we can definitely say it's not. We have not seen this element. So we'll see more like with the example, I think here.
Okay.
But before I go there, so one more thing that is there is to reduce the chances of collision. The actual Bloom filters are implemented with multiple hash functions. So we'll not say that we'll not use single hash functions. We'll use multiple hash functions so that we can reduce the chances of collision. So let's look at the example. So what it simply does is, so Bloom filter is just an array of bit set. So you will initialize all the bits to 0. Then what you do is you just hash the data into this bit set. So what you say is, let's say first you want to insert hello. So let's say you have some data set. First thing that we do is insert all the data set that you have with you.
Okay.
So let's say for spam detection, I will already have a list of, let's say, a few thousands keywords, which I know they are spam keywords, let's say.
Okay.
So what I will do is I will insert those data into my bit set. So I will hash that using a list of hash functions. So every hash function will give me a bit position. So hello, I hashed, and it says it needs to be inserted into 1 and 3. So we will set first and third bit in the bit set. When I index Bloom, it will basically saying 1 and 2. So it will set 1 and 2. So effectively, we will have 1, 2, 3, all the bit sets, bits set in this array.
Okay.
Corresponding to these two keywords.
So we are using k multiple hash functions, but we are storing the value in the same bit set only.
Yes, bit set is single bit set.
Okay. That is why it can lead to false positives.
Yes, yes.
Because
So
now if something on the hash one maps to 2, then we'll send the false true that this exists, where it will not exist.
now let's say if I try to search for a particular other keyword, then basically based on what bits it will map to, we will search those bits. If all the bits are set, then we will say it's a basically there is a probability that this word is present in the system.
Okay.
So now so in this, the size of the bit set was very small, so we ended up setting all the bits. But generally, based on how many keywords you have and what kind of error rate you are okay with, you have to do a design consideration that how much bigger bit set I need. So we'll go through that in the end.
Okay.
But this is the overall concept that you have list of words that are known things. You map it to a bit set, and now you have list of test data which you want to test. So basically, you just pass that into your test data, and that test data will basically, if using all the hash functions, it will give you multiple bit positions. If all the bit positions are 1, that means there are chances that this word is present. If any of the bit is 0, which means there is no keyword which is hashed to that particular bit set, which means it is definitely not there.
Okay.
So this section basically talks about what are the chances of having a false positive based on these values, where k is number of hash functions, m is the number of words that we have inserted into the Bloom filter, and n is your total size of the array bit sets.
Okay.
Okay, I think in this scenario, m is the number of bits, and
m is the total number of bits.
M is the bits, and n is the total number of insertions.
Where is, I do not see n.
N is here, and after n insertion, so n is the total number of words it has.
Okay.
So how it is trying to calculate is, this probability is little complicated, so we'll go slow. So first thing is, it says is, what is the chance of one bit being 0 after one insertion? So let's say you inserted a keyword.
Yes.
So let's forget k first. So let's just talk about one insertion using one hash function, and given an array of size m.
For
m.
So if there is one hash function, I'm going to hash. My hash will generate only one bit, or it can generate multiple bits.
It will generate one bit.
One bit only.
Yeah, I think should we note it down somewhere? Basically, so let's write it down. First is insert one word, probability of
if there are m bits, then probability of
probability of a particular bit being 0 in m bit array. So basically, basically what we know is that bit will be 0 if it is not 1, right?
Yes. So what is the probability?
Because we are setting a particular bit. So probability of setting that bit is 1 by n.
Yes, because it will be one of those m bits.
Yeah. So the probability of that bit being 0 is 1 minus 1 by n.
Yes.
Sorry, 1 minus 1 by m.
1 minus 1 by m.
Yeah.
And if we are using k hashes, so that will generate k bits.
Yeah.
And since all of these operations are happening together, then we need to multiply these probabilities.
Yeah. So basically, now if we are doing k hash functions, so after, we can say after k hash functions, we have to multiply all these probabilities that for every generation, we will not have this, we will still have this bit as 0.
Yes.
So k times, so it becomes like to the power k.
So with every new hash function being added, the probability is increasing.
Right. So this is the probability of one bit being 0.
Yes.
Okay.
This is what they came up with as well. After n insertions.
Correct. Now after n insertions, so this we did just one insertion using k functions. Now after n insertion, probability of that being 0 is again like after
multiplying this by n times. Yeah.
Correct. We just go here. Yeah. Now it says is, so that means probability of false positive is. So basically, if we have to see all bits as 1 for a particular value. So basically, what we will see is 1 at every value.
Yes.
So probability of 0 is this of a particular bit, but probability of 1 will be 1 minus this. And for every value to be present at that value, we will see this to the power k for each hash function.
Got it. For a single hash function, it will be 1 minus the previous probability.
Correct.
And so I think that is better way to represent it. Okay, you first we calculate it for a single hash function.
So we can say after
n insertions.
An insertion, we get this to the power nk. Now fourth step is basically, now if for doing one new insertion, if for which we want to detect false positive, we'll say probability of getting all ones via all hash functions. So probability of getting single one is single one via any hash function will be probability of getting 0 is this.
Isn't this the probability of getting 1 only?
Which one? This one.
1 minus. So after n insertions, probability of a bit being 0 is this. So then the probability of a bit being 1 is the probability that you just came up with now.
Yeah.
That doesn't mean it is false positive.
False. So you're right. What they are saying is this is probability of
getting 1.
Yeah, probability of getting 1 at a given position.
Yes.
So our probability of getting 0. So you're right. Basically, what you're saying, probability of getting all ones.
Yes, probability of getting all ones will be this multiplied by k. This raised to power k.
To the power k. So when do we get false positive, right? When we get everything as 1.
Yes.
So it might be.
It may be true.
It may be true. It may be false.
So basically, we are saying that this is the probability of getting a true.
Yes.
And probability of getting a true is equivalent to probability of getting a false positive.
Yeah. I think they are defining like that.
Okay.
Because you are looking for the probability that k different bits were flipped to 1. This is approximately equals to. This is approximation. We'll come to this. This they are defining as false positive. That if you get everything as 1, that is being defined as false positive.
Okay. Okay. That is fair assumption.
That is max basically. That is the cap.
That is worst case scenario. That is what will happen.
Yeah, right. Now I think for this approximation, what they are doing is so there is a formula basically that I1 minus plus 1 minus 1 by m to the power m
Hmm.
is equals to e to the power minus 1, sorry. So there is some approximation which says that based on, I think as m reaches infinity, this tends to e to the power minus 1.
M reaches infinity.
Yeah, as I'm.
So then, in real life scenario, this m has to be very large.
Yeah. So for larger values of m, I think this tends to reach e to the power minus 1.
Okay.
So based on that, they are just replacing this 1 minus 1 by m to e to the power minus. What they have done is, I think, multiplied by m and divided by m, this power. So this is nk by m and e to the power minus 1. So this is the approximation which we get.
Okay, and that gets converted to, so from there you can get the formula.
Yeah. So this is the rate of false positive. What they are doing is trying to find the optimal value of the k for which this function is minimum.
So you have to do the differential for this.
So they are doing differentiation and then they come out to this value. So they are not done the maths, shared the maths here, but
No, its differential will be this only, right? E raised to dx by dy of e raised to power x is e raised to power x only, right?
okay. So now if you put this value back into this, then you get the minimum error rate.
Okay, इसका differential I think we'll have to check, but let's assume this is correct.
Yeah. So basically this is to find the optimal number of hash functions for a given m and n. So basically this gives a formula between k, m and n. Now, if we have two values, we can find the third value. So generally how you start is basically you have a error rate in your mind. Like let's say I will say I am fine with 1% error rate. And based on 1% error rate, if I put that value in of error rate in this probability as a 1%, I will be able to find.
You will, instead of calculating the k, you will find it via the previous equation only, because you'll know n and k, n and m.
Yeah.
Got it.
So
where do we use it? I think it has very clear DNS also uses, right? Because in those cases,
DNS as in
when I'm trying to figure out whether this URL.
No, that is exact search, right?
That is exact search. Okay. Spam filter will definitely. Spam filter will use it.
We already talked about that one. There were others. Does not talk about this cases.
Other use cases are also there.
Not listed here, but we can see on this.
Okay.
So Redis has an inbuilt implementation where you can directly use this Redis CLI for with the Bloom filter. So they store the data in Redis and then you can directly use it. So Redis acts like your bit set. You have to configure your Redis with the parameters of n, m, and of error rate.
Does it provide us the capability of Bloom filter or just uses it internally?
It is providing you. So you are configuring it as a DS data structure inside Redis.
Okay. Okay.
Let's first look at the implementation. I think we'll come back to other things as well. So basically it is implementing a simple Bloom filter where it is saying m and k. K is your number of hash functions. I think it supports, for this example, only 1 and 2. And then data, it is being stored here. And n is set to 0. So if, let's say, if we have one hash function, then it is just doing the hash of the element modulus m and storing the value in the data, setting that bit. If it is 2, it is using 2 different hash functions, storing in the data set, incrementing the total number of values. This is the insert function, simple insert. So for insert, you have to set every bit. using all the hash functions. For search, you first hash it, try to see if data is 0. If it is 0, then it is not in the Bloom filter. For k equal to 2, I think they are taking different example where hash using both the functions. If both the values are not 0, which means both the values are 1. If either is 0, then not in Bloom filter. If all are 1, then it is saying it is there in the Bloom filter with this probability. Might be in the Bloom filter with the false positive probability of this much.
Okay. Got it. So you will use this in cases where you are okay with some probabilistic answer, or very sure that this is not present.
Yeah.
That case would be, I can think of, I think presence checks.
Presence check, risk checks, right? Like something is risky or not. So you can say it is risky with the chances of how much percentage, and then you can put a threshold that this if it is goes above certain threshold, then you can
got it. So this can be used in combination of an ML model for risk checks.
Yeah.
Okay.
I think you can have multiple Bloom filters, right? Like as in I can have a Bloom filter for parameter 1, parameter 2, parameter 3. Like let's take an example, right? So let's say if you are building some kind of software system where you receive a request, and in request you have multiple parameters, and different parameters might have different values. So for every enum, let's say you can create a separate Bloom filter, and you get multiple outputs, and then based on output of all the Bloom filters, you can finally predict, okay, what is the total chance of having this overall request as a risky. So without much calculations, it's very, very fast to calculate whether it is risky or not, and then you return the error rate. You can decide to reject.
This was much simpler than we thought.
Yeah. Like if you look at the complexities, insertion is order of k. K is number of hash functions, because we just have to calculate k bit values and just set it. Search is again same, because we have to just check the k bit sets. And space complexity is of the order of m. So based on your space requirements, space restrictions, you need to decide on these values.
Okay. Cool, then I think this is it for this video. We'll come back with more such videos in future.